It's really a great thrill to be here to talk to you about our research. It's basically catching malware in mass, DNS, and IP style. And my name is Dhia, and I work at OpenDNS as a senior security researcher. This is Thibault, our guru in data visualization, very smart guy. And then Andree, the director of our network operations. Very smart dude in terms of internet and ASNs and BGP prefixes. Let's look at the agenda of today. So we'll start with an introduction about OpenDNS's global presence, and then we'll dive directly into the main parts of the talk. The first one is about catching malware from a DNS perspective, and the second one is about looking at the IP infrastructure. And then within the use cases we'll discuss, we'll support that with the 3D visualization engine we have, which we open sourced this week. So OpenDNS has 22 data centers across the globe, four continents, and then that allows us to see a lot of traffic, mainly DNS of two types, recursive and authoritative. And that allows us to build a lot of useful models. Now, the first part will be about caching malware from a DNS perspective. But before that, let's look at the kind of the crimeware ecosystem, mainly the mainstream crimeware of today, to give like some foundations. So here we see four components mainly. Like the top part is when you visit a website that is compromised or delivering like malicious ads, then you get some exploits, like scripts running on your machine, seeing if you have any vulnerabilities, and if that succeeds, then you'll have a malware payload dropped on your box. And then that malware will try later to phone back to some CNCs. Usually they are domains, and in this case they are hosted on fast flux proxy networks. This is the focus of this part today. And we'll be focusing on the ZBot one, hosting mainly Zeus domains. And they have a characteristic of a TTL of 150 seconds. And that's the focus of today. A little armadillo there. Now, a little bit about our research process in this part. So we start focusing on these ZBot fast flux proxy networks. Like we said, we use two methods. One is using Hadoop because we have a lot of data. Most of it is on HDFS, and the other one is using the streaming DNS traffic because we have streaming authoritative DNS traffic coming in, so we can also use that. With that, we can identify the malware, and then we also discovered Pony Panel hosted on one of these proxy network domains. And then at the end, we'll share some stats about the botnet and the samples and the clients. So what is fast flux? I'm sure most of you know about it. It's a domain resolving to a lot of IPs scattered around the world, or a single IP with a very low TTL. Now, if we're talking about a fast flux proxy network, it's a cloud in the middle with a lot of infected bots. They act as a shield or intermediary for communication between the back-end CNCs on the left and then the targets on the right. Targets is usually machines that you try to infect because they have valuable information you want to steal. And then the communication will happen in two directions. So if the targets get infected, they will phone back to announce their existence, their status, or some exfiltrated data. And the back ends, if they want to push extra payload, they will drop it on the bots, and then further later, it's going to be dropped on the target machines. In this case, we're looking at the ZBot fast flux proxy network, which, as we said, has a TTL of 150 seconds. Now, we mentioned Zeus. What is Zeus? Most of you know about it. It's one of the most advanced crimeware toolkits around. Hey! There you go. These are the Zeus guys. So they're going to load us with Zeus. So Zeus is one of the most advanced crimeware toolkits around there. You feed it with an input, which is usually a configuration file, and web injects. And the configuration file would have the config URLs, binary URLs, and drop zone URLs. And then you give that to the builder, and it will spit out the binary file. Now, on the other side, you have a control panel, and that one will let the adversary control his botnet, because he will see what kind of machines got infected, and he can monitor his gains, in other words. This slide shows you a timeline of the Zeus variants that we saw over the years.
Be quiet. Nobody really cares about Zeus.
I know. I care about you. I do care about you.
You know what we care about? We care about our new speakers.
Thank you.
How about some love for the new speakers? Congratulations, guys. Here's to DEF CON.
Cheers, cheers to the crowd. Cheers to DEF CON.
Congratulations. Cyber.
Thanks a lot.
I actually haven't had
awesome.
breakfast this morning.
All right, thank you guys. So, yeah, we were talking about Zeus.
Move on.
I'll call it Venus. Okay, Venus. We are in Vegas, so we're dealing with a lot of Venuses. So, okay, so Venus has a lot of CNCs. They're hosted on compromised sites, bulletproof hosting providers, and also fast flux botnets. And that's the focus of today. Now, Venus also delivers CNC URLs, config files, binary files, and drop zones. Now, how do we catch these CNC domains? We have two methods, as we said. One is Hadoop based and one is streaming DNS based. For the first one, just for your reference, we use PIG, which is kind of a language that allows it to process the data stored on HDFS, and we extract from, let's say, a set of files within a certain time frame. We'll extract fast flux domains with a TTL of 150 seconds. And then we build a graph, the domain to IP bipartite graph, and then we extract the largest connected component. That one will give you empirically the bulk of the domains and IPs. The other method is using the stream, and it looks like that. So you have like a lot of fields that are of interest to you. It's faster than doing like batch processing from HDFS. But you have to have your own filters and heuristics to catch what you need because it's going fast. So for that we can start with a seed of ZBot domains. We milk them for IPs over constantly. So you build a pool of IPs and then you have the stream coming. So then you can grab the domains that have an IP or name server IP within that pool. So having had that, what we can do is do some more investigation using data visualization, and Thibault will tell us about it.
Thank you, Dhia. Yeah, so Dhia just explained two different methods to extract some graph data linking ZBot CNC domains with their IPs. So first let's take a look at how we're going to visualize that. First we have the source data, which is pretty much the logs, like the stream. Then we can convert the data using our own Python library. Then we're going to visualize it and manipulate it a little bit. So this is Semantic Net library. This is a small graph library that we've developed at OpenDNS. So as you can see, it's fairly simple. It's in Python. You can import the library here. You create the graph. You can create a couple of nodes and then connect them using the node keys. And then you can have types and different types of attributes in the graph. That gives you the equivalent, of the diagram you have on the right. Now let's take a look at how it looks like, once we've extracted this data from the logs. So what we're looking at here, thank you. So what we're looking at here are the Zeus CNC domains in red and the IPs in blue. And then finally we can play that animation over time. It's a period of 3 months. So we can notice that we have a growing pool of IPs and domains. The IPs keep getting recycled and the domain hop from one IP to another. So the way we actually constructed this animation is we took all the domains in there, the IPs that were mapped to. The first time we actually saw the IPs in the logs, and then we monitored that over time. And finally we can create a timeline to see all the events and play it on the 3D.
All right, thank you, Thibault. Thank you, Thibault. Now, thanks to this investigation using visualization, and that helped us basically confirm a few things. The next step is to figure out what are these domains used for. So it's okay to catch these domains, it's relatively easy. But we see here that they are multi-purpose. So on the left you see they are used by Zeus, the generic variant, Citadel, Kins, and Ice9, and delivering the 3 types of URLs. On the other side you have Asprox, which is a click fraud botnet, and also phishing and miscellaneous cases. So this slide, you'll find it in the white paper, so I'm just putting it here for reference. We saw Zeus URLs, also Citadel URLs, hosted on the fast flux domains, also phishing URLs, and Asprox, a lot of click fraud traffic using these CNC domains. And then there's this interesting case. This is what we call a DDoS bot, phoning home using one of these domains. Here it's announcing the operating system it's running. And furthermore, what we did, these are some more cases of other malware using the domains. Now, this one is an interesting case where we discovered a Pony panel hosted on one of these fastflex domains. Now, Pony is an info stealer. It tries to steal passwords and information from a variety of applications on your machine. And then it's delivered via exploit kits or spam. This is how it's advertised on some hacking forums. And then this is how it's detected by some AV vendors. Now, if we look further into the structure of the website, we'll see some interesting things. The database here, for example, has a character set of Cyrillic and the time zone is Moscow, which is an indication about the origin of the writer or the user of the panel. We also see that it has the list of all of the applications it tries to steal passwords from. Now, just some snapshots for your reference. You can find them in the white paper and a few more here. Now, the next thing we did was to search for some keywords we found on the panel and try to find anything related or similar. And we found like this website that is hosting another piece of malware, and this one happens to be an Andromeda botnet malware. And then we looked more for more like websites having the same structure as the original panel. Now, let's look at the domains and how they are, what's their structure or like where do they come from. So they are abusing mostly .ru and .su, so this is another indicator about the origin, the geographical location of the actors, I would say. And then if you look at the bots, where are they located, you'll see them mainly in Russia and Ukraine. So again, this is an Eastern European operation to some extent. However, if you look at the clients looking up these domains over 24 hours, you'll see they are mainly in the United States. Well, you could say that's because OpenDNS has mainly traffic in the United States, but also maybe because a lot of valuable information is in North American machines, mainly like banking information. Because again, Zeus is a banking Trojan, so it would make sense. Now finally, what we did with these fastflex domains, we tried to see what kind of malware is phoning back to them. And we saw with no surprise ZBot is the top list, and then also Upatry. Upatry is like a first stage downloader that will bring down on your machine extra maliciousness. And in this case, it's been involved with Zeus Game Over, like a very virulent variant of Zeus. So in summary, about this part dealing with DNS, we shared with you information and research about the ZBot Fastflex proxy network. I mean, Fastflex has been around, people know about it, but in this case, this Fastflex proxy network is alive. It's very active, it's multi-purpose, used by a variety of malware, and it's mainly hosted in Russia and Ukraine, targeting machines in North America, and abusing mostly .ru and .su. So that's kind of interesting to look at this very current threat. Now, having covered the DNS style, how about the IP style? Because that's kind of the complement of the study here. So for that, we looked at two different granularities. Usually IP reputation systems, they assign scores to IPs, prefixes or ASNs by just counting the number of domains and IPs living on those structures or entities. In our study, we wanted to enrich that because that's kind of weak sometimes, and we wanted to look at the granularity in one case finer than the BGP prefix, which is sub-allocated ranges. So let's say you have a prefix of /16, you want to look at smaller granularity, like /28 and 29. On the other end, you want to look at the ASN graph, because that's larger than just a single ASN if you're just counting numbers within that ASN. And that gives us like a lot of valuable intelligence, and we were able to build some really cool models. So the first one is about the malicious sub-allocated ranges. The investigation process is always trying to start with domains and IPs, and in this case, we investigated the sub-allocated ranges and we did the fingerprinting of them to see what kind of servers they are running. Then with that, we were able to follow the TTP of the adversaries, like the way they operate and how they bring the infrastructure online and the timing. Then after that, we were able to generalize the predictions to block IPs before they start delivering the attacks. And that was really groundbreaking. And then over time, we are able to see the shift in the operations of the adversaries. So we'll start with this example that we covered over several months. This was about nuclear exploit kit domains, and they were abusing OVH Canada for several months. They were basically reserving IPs, certain customers, suspicious ones, and these IPs, like they were /28, 29, 30, brought online all at once, all together, and that lasted for several months, delivering like nuclear exploit kit domains. After a few months, they shifted to a Ukrainian hosting provider, and that lasted for 7 days. In this case, however, they shifted MO, because OVH Canada is in the air and space, and you're able to grab some information about the customers reserving the IPs by looking at the whois. Ukraine is in the RIPE space, and that's much difficult because RIPE is kind of scarce in terms of details. Also, the IPs were brought online in one at a time and also in randomized fashion. So this is somehow a way to evade kind of detection heuristics. Then they shifted to another provider. This one is in Russia. Oops. So the Russian one was keeping the same MO, and then they went back to OVH. In this case, it was the same people reserving the IPs, the ranges, but the MO changed a little bit. Now they are using recycled IPs. IPs that hosted old content or have a rather clean score. And again, these are like ways to evade IP reputation systems that a lot of security vendors use. So these guys are really smart. They react and adapt and kind of try to evade you and give you a hard time. However, over all of this period, the name servers were still being hosted on OVH IP space. So somehow you might think name servers are much more difficult to prove to be malicious, whereas the domains themselves serving the nuclear exploit kits, they're easier because you have the landing URL, if you can grab it, and that's kind of easier to prove it's related to a certain exploit kit. Now this animation shows you the ephemeral pattern of these domains. You have a lot of them pop on a single IP. It's kind of a fireworks pattern here over time. And they just like die out after a few minutes or a few hours. So it's a very interesting case here of registering domains, delivering the attacks, and just dying and never coming back. Now we did a blog back in February about the study, and we also took down a lot of these domains in cooperation with the research group Malware Must Die. Now having said that, how can we push this further and kind of give a hard time back to the adversaries?
What's your prediction for the fight? Prediction? Yes, prediction.
Oops, hold on.
What's your prediction for the fight? Prediction? Yes, prediction. Pain.
Okay, this one is one of my favorite ones. So Mr. T is inflicting pain trying to inflict pain on Rocky. We'll try to do the same on these adversaries. So let's look at this case here. This automatic thing is giving me a hard time. Okay, stop there. So we looked at these reserved IP ranges over time, and we see that they reserve 28 ranges in December, and within them 136 IPs, 86 are being used, and 63% of them are malicious. And you see the trend growing. Like in February it was 92% maliciousness. The point I'm trying to make here is that these guys reserve these ranges, they deliver the attacks with a high percentage on these IPs. So it's no coincidence, they're not using them for other purposes. It's specifically targeted in trying to abuse the hosting provider. Now the point here is that if you look at the BGP prefixes where these IPs are living, you'll see it's a very coarse granularity. It's like a huge one, 17/18 and /19. You got a lot of IPs to look at in these big ranges. So you cannot get that nice laser sharp view of what is going on. Whereas if you do the IP ranges finer study, that gives you a lot more visibility into what's going on and how the bad actors or adversaries are thinking. Now the other interesting thing we did is try to fingerprint these IPs. When we discover them, we know they are reserved by the same guys. They had the same exact server setup. So the first one is the Ukrainian and then the Russian. And it's the same also with OVH Canada. So the point here is that by looking at the reserved IP ranges by the same guys and also the same fingerprints, And we saw over time that they always exclusively serve the attacks. Again, this is a pre-established operation being carried over and over again, and it's still coincidence. So it's kind of interesting to see that, knowing those facts, we're able to predictively block these IPs before any domain start resolving to them. So that's kind of the breakthrough in this study. Now over time we also saw that the adversaries were shifting MO. Now they know what we know. So the trend that we saw growing is that they started abusing compromised domains. Like domains that were benign, they just go and inject malicious subdomains under them. And we did a study about that. So we started detecting that, and we collected the IPs that where these subdomains were being hosted. And we had like a list of all of the most abused ASNs. We were also looking always at a finer granularity than the big ASNs. So we looked at small scale providers, trying to see if they were abused or rogue, like bulletproof hosting providers. And then over time we were able to kind of see the evolution of the techniques and methods of these adversaries, and that was quite interesting. So in this case, these malicious subdomains were delivering exploit kits mainly, and they were dropping Zeus variants if the infection chain succeeds. And GoDaddy was the most abused in this case, unfortunately for them. Now looking at the top abused ASNs, again, OVH is on the top. 18% of the IPs were malicious. Were from OVH within a sample of malicious IPs. And we also have ASNs scattered across Europe and North America. Now this table here summarizes the evolution of the TTP of the adversaries. This one is really cool. I like it because it kind of gives you the whole picture. So before is like a few months ago, and now is the current state. So they used to abuse like registered domains under certain CCTLDs and exclusively use them for the attacks. Nowadays they complement that with abused subdomains, abused domains under which they inject subdomains. The second thing is that the IPs that they reserved, they were all exclusively for attacks. Nowadays they complement that with recycled IPs that hosted legit stuff. And third, they used to bring the IPs all in contiguous chunks, all together. Nowadays it's like randomized, one at a time, whenever they feel like it. Again, it's like evasion techniques that are clear in this case. And finally, we said that they used to abuse OVH Canada, and it was possible to take advantage of the errand who is, because it tells us the customer reserving these IPs. Whereas now they are using OVH Europe, and it's in the ripe space, which is scarce in details. And on top of that, they are using different countries' IP pools. So this is clearly a very interesting way they shift operations and methods. But we were able to kind of follow them over time. This one here is about the fine-grained hosting perspective. So these are like small-scale bulletproof hosting providers, mainly serving maliciousness. This guy is King Servers here. Another one in Russia, Ivro Hoster. Another one in Bulgaria. And this one, Electric Kitten, unfortunately abused in North America. And then a few more for your reference. And finally, what we did here is look at the subdomains, like the labels that are injected under, let's say, GoDaddy domains. Because usually it's like 3 labels. You have, let's say, police.homebusiness.com. So the top used ones in this case were police and alert police. We thought maybe this is related to the theme of the attack, and that was the case. Like the first 2, they were used for browser-based ransomware, which is a web page that pops in your browser telling you, hey, you've been looking at some weird stuff, porn and whatnot, and the FBI or the local police will come after you if you don't pay a ransom. You can kill it just by, killing the scripts or killing the browser process. It's kind of a nuisance more than a threat. But still, the labels were related to the attacks in this case. The rest were mainly randomized but extracted from English-like dictionaries. All right. So I know I covered a lot, and it was basically a DNS perspective, an IP perspective by looking at sub-allocated ranges, and then we mentioned earlier the view of the ASN graph topology. So before we get into that, we want to know a little more details about the internet structure.
Hi, Dhia. Oh man, you gave it away.
I ruined it.
So yeah, the next section we'll take a closer look at how we can use ASN relationships and relationships on the internet, different prefixes and so on and so forth to detect more malware. But before we do that, we need to make sure that we're all on the same page and understand how the internet works. I'm sure you guys all knew, but when we talk to different people, we get different replies. For example, if I ask my dad what the internet looks like, he'll probably turn around and point to the corner of the living room where this DSL modem lies, or cable modem. Or if I ask a sales guy what the internet looks like, I'll probably draw like a magic cloud and writes internet in it and may use fancy colors. And then I walk on to the next room, which is where the IT guys sit, and they're always cool. And I ask them, do you know what the internet looks like, or can you explain it to me? And they start to giggle because it reminds them of this one episode of the IT crowd, where they got to borrow the internet for a day from the elders of the internet. And it was this magic black box, and it had a blinking light on it. And as you can see, it's wireless. But obviously the internet is no magic black box. In fact, it's much more beautiful. I guess if you wanted to paint a picture of the internet, this is sort of what it would look like. We have a few more, like as Dhia mentioned, we do a lot of visualizations as well. So in the next few slides you'll see a few more. But the internet, obviously, as you all know, it's just a network of networks, and it's a graph, and we like graphs. So in this picture, each dot represents an autonomous system, and an autonomous system on the internet is basically one organization. So OpenDNS is an autonomous system, Google is an autonomous system, AT&T, Verizon, so on and so forth. And each of these autonomous systems is identified by a number, which we call an AS number, or sometimes people call it an ASN. And then each ASN has been allocated or announces one or more IPv4, IPv6 prefixes. And it can just be one, but it can be several thousands. But that's basically how it works. I'm sure you guys all knew that, but now we're all on the same page. So we have all these ASNs, they're all connected to each other, or at least one, because you need connectivity to the rest of the internet. So now imagine that you're on the left-hand side of this graph and you want to go to the right-hand side. You need to know how to get there, and that's why we need a routing protocol, which is BGP, which will distribute all this information. And BGP in itself is a really interesting talk as well, especially what you can do with that. It's a little bit out of scope for this. But basically what we're doing is we're building a graph using BGP data. You can find all kinds of public data, route views, RIPE. We use our own data, BGP-Mon. Just so you know, there's about 500,000 prefixes out there and about 48,000 ASNs. So you can build a really, really large graph, which actually has some challenges when you start to visualize that. These are just some references. But yeah, this is how you would build the graph. Just focus on the last line, which are two items in there colored in red. So one is the actual prefix, 67.215.94.0/24. And then this next part is the AS path. And that shows how ASNs are connected to each other. And you can infer all kinds of interesting data from that. In this case, the one on the right-hand side, 36692, is OpenDNS. It's connected to 2914, and from that I know, oh, well, that's NTT, so OpenDNS buys from NTT, and so on and so forth. You can see all kinds of interesting data from that. And then basically we produce a graph, and then we can use that for further analysis.
Thank you, Andree. Yeah, absolutely. So Andree just described how we can create this graph data set, from the BGP routing tables. So same thing, we create with the same concept, the same library, we can create a graph data set. And then what we need is to use very, very simple particle physics. So even if you're not really a math nerd, don't run away. It's very simple. Essentially, the concept is very simple. You take your graph and all pair of nodes that is connected, it's going to attract each other to a certain point. And every pair of node that is disconnected is going to repulse each other. So you can see here two different forces here, the attractive force, the repulsive force. They all depend on distance, and they can be manipulated with the constant c, which is like multiplied by the square root of the area divided by the number of nodes. So it's a lot of complicated words just to say, that is, factor the density, and we can control the density of the layout just by this constant c. All right, so how it looks like. We start with all the nodes in the same position, in a random fashion, or in a cube, in a sphere, it doesn't really matter. And then we start running the particle physics. So what you see here is pretty much the explosion, the graph expanding itself in 3D space. So all the nodes are connected together, are going to stick with each other, pretty much stay with each other, and all the nodes that are disconnected are going to repulse. So you can see that the layout kind of looks like a molecule a little bit, which makes complete sense because the force-directed algorithm is inspired by electrical forces, also like the forces between celestial bodies. It's not exactly the same model because it's way too complicated to implement on the CPU, but still, it's very close. And then finally, after a couple of iterations, you can see that the nodes like stop vibrating. This means that all the forces are becoming even, and that usually the graph has reached the equilibrium state. However, this is really cool, but doesn't really work well and scale well for the ASN network. So we have to take advantage of parallelization. So essentially, we run the same thing on the GPU, and we use a library called OpenCL. Actually, it's more like a specification because it can be implemented in FPGAs, GPUs, CPUs if it runs on emulation. But anyway, essentially, OpenCL is very simple. It exposes a couple of work groups and like work items, which are pretty much cores and threads in the GPU, and different kinds of memory, like global memory, local memory, private memory. Private memory is pretty much the registers, and global memory is the global memory of the GPU. So essentially, it's like a trade-off between, the ease of access of the memory and like the performance, because the private memory is actually very fast to access. Okay, main point. Why are we doing this? You look at the pictures, like, okay, that's pretty cool, but what's the point? The main point is the layout is data-driven versus user-driven. As you can see, the layout depends on the forces, and the forces depend on the connections between the nodes. So the result is a layout that completely depends on the data structure that you're looking at. It is much closer to what I like to call the natural shape, of the data model that you're looking at. We take advantage of the GPU for acceleration. GPUs have become insanely fast, to operate like vector-based operations. So it would be a shame not to take advantage of that. And finally, main point, humans are so much better at processing shapes and colors rather than, text data. So let's see how it looks like. We'll take a look at the whole process. So we take the whole ASN graph, and at first, as I said, it's like placed in a random fashion. Doesn't really make sense. It's a big mess, of ASN nodes rotate around. So on this layout, you don't see the edges because usually the process runs offline. It's just, for the performance, performance case. We're trying to go as fast as possible here. And then we start the force-directed process. So as you can see, it's a very heavy process. Like every iterations, I think I had like a 0.3 iterations per second. So like close to 3 iterations per second. No, wait, 0.3 iterations per second. So that runs on an NVIDIA GTX 550. It's like a graphic card is like 3-4 years old, something like that. And then that runs for an hour. And the result is something like this. So as you can see, Andree is going to give us his expertise over this graph, but as you can see, like right away, is that the ASN network is very densely connected and has a very, very strong core. Very strong core. And then we have kind of a sparse nodes around. And then we can extract, create like very high resolution pictures. Looks like this.
Yeah, and if you are a network geek or you just like pictures, this is sort of what the internet looks like. And in network engineering, we often use sort of the loosely defined terms, tier 1, tier 2, tier 3, where tier 1 is sort of the core of the internet. There's only a dozen or so of them. Those are level 3, NTT, AT&T, some of those. And then around that, so those are the pink ones, are sort of the larger regional networks. And then at the edge is where you have the tier 3s. And those are typically web hosters, but also people like OpenDNS and Facebook and people like that who don't provide connectivity to others. This is another picture where you can really clearly see that. But you can in this picture you can really see the different clusters which show sort of the regional networks. And typically these different clusters represent different countries. This is a animation of the internet in the Ukraine. And it shows that the Ukraine is relying on only a few sort of upstream networks. So if you wanted to do something bad, if you could be able to take that autonomous system out of rotation, then you would probably be able to cut off a significant portion of a country. And we've seen similar things like that in the past. During the Arab Spring, we saw Egypt being taken offline. Well, that's only possible because there were like 3 or 4 major carriers in that country. And more recently in Syria, where there's only one national telco, so if you shut that one down, the whole country is offline. It's sort of ironic, because you think about it, the internet was made to survive nuclear warfare and blah, 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 so no single points of failures. But the way the internet is built in a lot of countries is that they're still relying on one or two networks, and if you take that one out, you'll be able to take down a significant portion of it. So I think this is a really good picture to represent that. So.
Yeah, this stuff is awesome. So thanks Thibault and Andree for this perspective about the ASN network. Now the thing is, we're looking after maliciousness. That was the core of the research. Now how can we use the ASN graph to extract the maliciousness we're after? So we're introducing the concept of suspicious, or actually sibling peripheral ASNs, and then we look for suspicious ones. We look at domains and IPs, and then we study the fingerprints and the ranges that we are focused on. And then that allows us to build relationships between the ASNs by considering the ASN topology, the ASN graph topology. And then thanks to that we can build a model. And finally we are proposing, we'll talk about it later, a novel approach to verify the relationships between ASNs by monitoring BGP outages. This is kind of a breakthrough in this case. You'll see. Now the malware we're looking at was some kind of a Trojan here, hosted on /23/24s. And we took a sample of these IPs. This is how it's described on VT by some AV vendors. And we took the sample of IPs and we did the fingerprinting again, and we saw the interesting case of the previous study, which is all of them have the same server setup. So we have two clusters of kind of server setups here. So this is an operation set up in bulk and in advance. Now looking at the ASN graph topology, we introduced the concepts of SPN. SPN is sibling peripheral nodes. Sibling in the sense you see the top ASNs, they share the same upstream provider at the bottom because they rely on him to advertise their prefixes. So they're kind of brothers and sisters in a way. And then peripheral because they have no downstream providers. So they are on the outskirts or the periphery of the internet. Now we look for suspicious ones in this case. So this is a subgraph we took, a snapshot from the Ukrainian-Russian IP space in January, and we see a bunch of these ASNs, sibling and peripheral, hosting, because they are in red, the malicious payload, and one of the parents is also doing the same. A month and a half later, one of the parents detached itself, it stopped advertising the kids' BGP prefixes, and more of the children are now hosting the malicious payload. Now the thing is, we looked at the entire pool of IPs and we saw a lot of domains hosted on them. And we also saw that the payload URLs were live on the IPs before any domain starts resolving to them. So the point here is that this is an operation established in bulk in advance to deliver this Trojan payload. And the thing is, we saw this across different kind of IP spaces. So this was a case we are talking about, but we wanted to scale it up and use it like on a global fashion. And here comes the introduction of the SPN from Thibault's perspective.
Sure. I'd like to give like a visual approach of the SPN model so we are all on the same page and make sure we're talking about the same thing. So when we look at the graph, when we study graph topology, usually we're interested in different features. One of them is the degree of the nodes, the number of connections. And then we can classify all the nodes depending, on the number of connections that they have. So as you can see here, there's a blue node. It's called a sync node because it only has like incoming connections. Then you have a green, it's called the leaf node. It only has one outgoing connection. And then finally, the red ones are like the source nodes. And the source nodes are like ones like two or more outgoing connections. And the white ones are pretty much the other ones that don't really respond to the same criteria. So when we apply the SPN detection, this is what happens. Essentially, we keep only the peripheral nodes, which are the nodes that don't have any incoming connections. So it's like, as Dhia said, the outskirts, like the suburbs, I would say, of the ASN networks. And then we keep their parents. And the result is pretty much a graph with all the peripheral node and their siblings, and including their parents as well. So we can apply this on the same data set, for example, in Ukraine, which is the relevant ASN network in this case. So it's the same data set before, same color code. So you can see all the leaf nodes like kind of around, all the peripheral nodes, the red and green ones. And finally, when we apply the filter, when we extract, the SPN graph, then we pretty much prune the core of the ASN network. And then we can select a couple of candidates, like this one, for example. And this one has a couple of leaves connected together to the same parent. So that would be like a very interesting candidate for us to look at. Now, if you look at the whole ASN network here, I mean the Ukrainian one, you can see that there are a lot of candidates. So another better approach to actually start from one known malicious or suspicious ASN and check if it has siblings, if it's a peripheral node, if it has siblings.
Okay, cool. So I want to do one step back and sort of summarize what Dhia just said. So what we found was basically a whole bunch of prefixes that were hosted by different ASNs, and you can see them here. The ones in red were hosting similar type of malware, and when we scanned them, they had the exact same fingerprint. And at some point, some were used for hosting malware, but others not yet, but we knew they were coming on in the future. And why is this interesting? Because typically we look at blocking malware maybe on a domain name level or an IP name level, or sometimes even on a complete AS level. But what appeared to be the case here is that these bad guys, or the guys who were hosting this, were actually hiding in different ASNs. And typically an ASN is one administrative domain, right? So in this case it seems like this whole group of ASN is one administrative domain, owned and operated by one guy. So we were like, okay, how can we prove that? So that's sort of the presumption, that's our hypothesis. So we figured, well, maybe if one of these ASNs goes down and they were actually owned and operated by the same guy running on the same infrastructure, then all the other ones must go down as well because they're running on the same infrastructure. That was sort of the idea. So we were like, okay, how can we prove that? So we looked at BGP outage data. So we used data from the guys at bgpmon.net. They have like 2 years worth of all the outages on the internet that you can query. How does that work? How do they get that? You can look at update messages and withdrawal messages. Those are sort of the two main BGP messages. And I'm not going to go into detail, but basically if you look at a withdrawal, then the prefix is unreachable, and then an hour later there's an update. And you do that from hundreds of routers at the same time, and then you basically correlate when there's an outage. So that's what we did. And we looked at all these ASNs and see if there were overlapping outages. And this was the result, which is a lot of text, I know, and a lot of numbers, but basically it's a table showing all the ASNs and the overlapping outages at the same time. And the main takeaway here is that the numbers are really high. So this is over the course of 6 months or so. So I'm zooming in to three ASNs here. One is the upstream ASN, because obviously you can say if the upstream one goes down, the one that's called 48361, then all the rest must go down as well. It makes total sense. But what we see in this case is that the upstream one provider maintained up and running for most of the time, but the two other ones, which are just two of the child ones, went down 22 times at the exact same time over the course of 6 months. So here are two examples. This is just for the month of July. Again, it's a bunch of text, but you can see that, or what it shows is that two of these ASNs went down at the exact same time, sometimes for 497 minutes, 479 minutes, 33 minutes, 63 minutes, exact same start time, end time, duration. So what does that mean? I think with this we sort of prove that, you know, these different ASNs are actually owned and operated by the same guys. They just have multiple ASNs and hiding behind that. So we're sure that they're relying on the same infrastructure. Could be just the same data center, could be the same router or switch. That switch goes down, the thing goes down. But we're definitely sure that the same organization. And in fact, you might even go further and say it could even be hosted on the same physical hardware, the same servers have multiple IP addresses running on the different ASNs. But in any ways, it's a unique approach to find these sort of sibling ASNs that could be related. And it also allows us to quickly, if we know a bad ASN, we'll just run the script. It will tell us which other ASNs are related or have the same outages. And we can then zoom into that. So that's pretty cool, I think.
Thank you, guys. So, in conclusion, what we shared with you was research about catching maliciousness on the internet from a DNS and IP perspective. For DNS, we looked at the ZBot fast flux proxy network. We described how we catch the domains and how it's multi-purpose and highly used by current malware. And then on the IP side, we looked at two granularities, the sub-allocated ranges and the ASN graph topology. We introduced a novel approach to monitor relationships based on the BGP outages, and we also proposed the model of SPN, the sibling peripheral ASNs, which is also catching related ones that have the same kind of suspicious purpose. And finally, we open sourced our 3D visualization engine that Thibault described this week. So it's on GitHub. You should use it and contribute back. It's all for the community, and we'll be very happy to see you contribute back. Some of the references we used, and then you can follow us on Twitter to keep in touch. And thank you again, and if you have any questions and we have the time, feel free to ask.